The webinar will begin shortly. Please remain on the line. All attendees are in listen-only mode.
Thanks for joining us this morning. The webinar will start in about 2 to 3 minutes. On behalf of Confluent, I'd like to welcome you to today's webinar. My name is Clark Patterson. I'm the head of product marketing here. Our speaker today is Michael Knoll. He's the product manager for all things streaming at Confluent, and he's going to talk to us about best practices for selecting a streaming platform or solution. At the end of the presentation today, we are going to do a Q&A panel. So I encourage everyone to enter questions into the chat window in the GoToWebinar screen. I will come back on after Michael's done talking. We'll triage as many of those questions as we can, giving you a lot of time. For those that we don't get through, if there's an abundance of them remaining, we will aim to follow up with a post on our blog answering some of the more relevant ones to today's conversation. So with that, I want to pass it over to Michael, and he'll run through, and I hope everyone enjoys the webinar today. Michael?
Thank you, Clark. This session on selecting a stream processing technology. My name is Michael, and in the next few minutes, we'll be talking about stream processing in practice. So before we start, let me give you a heads up. This talk is both narrow, in the sense that we will be focusing on technical functionality, but the talk is also broad, in the sense that the talk is meant to be broadly applicable for the majority of users and attendees. So, for example, for that reason, I will not be doing any specific tool A versus tool B comparisons, because there are just too many of those. So, what is the goal of this session? The goal is primarily to help you make your own evaluations and decisions when being faced with the question, well, which stream processing technology do I need at my company or for a certain use case? So what I'll do is I'll give an overview of today's feature space for stream processing, and I will highlight a subset of key features in this space. Now, we have some time constraints apparently, so we can only look at some of these. Now, this is the 5th talk in the series, and we've learned in the past talks that stream processing is not just about real-time processing. It is a much more generally applicable programming paradigm. However, because most of our users and attendees express their interest in the real-time part, in this talk we will have a slight bias towards the real-time functionality. So, and lastly, before we start, I'll also mention briefly what will not be in scope. So here it's about a practical guide to selecting a piece of technology. What we will not cover is how do you actually go about figuring out what your expectations are and what do you need. So this is left as an exercise to the audience. And lastly, there's also the question about cloud and cloud technologies. Now, largely, stream processing in the cloud uses the same technologies or features than on-premise technology. So in this session, we will not distinguish between cloud and on-premises, and also we will not cover any cloud-only technologies. Now, for those of you who are joining us for the first time in the series, this is actually the 5th talk in this series. There have been a few others already. There is a link in the slide that you can follow if you want to see the recordings of the previous ones. And there's also another one upcoming mid-December where we're talking about streaming in practice. So this is the preamble. Let's get right in. So what's the agenda? So we'll start with a recap on what stream processing is very briefly. We will talk about the 3 pillars of stream processing in practice, which are, in my opinion, cross-cutting aspects that I want to specifically highlight hence, we discussed these in a separate section at the beginning. And you'll notice that these will touch upon many of the criteria and dimensions we will talk about later in more detail. Then we talk about, as I mentioned, these selection criteria, and then we'll have a brief wrap-up at the very end. So let's start with what is stream processing. Stream processing starts with the data. And as we've seen in the previous talks, the streaming is based on a log or a stream. So what is that? It is an ordered sequence of data starting from 0 all the way to the very end, where new data is being appended at the very end of the stream, and then readers, such as stream processing tools, can take a look at the stream and start processing it, which is stream processing, which is simply processing the data in a log and in a stream. Now, what's important to understand is that stream processing is not necessarily real-time only. You could do both batch as well as real-time processing on top of streams. So batch would be a model where you would start reading a chunk of data in the stream, you would process this, and then you would stop, and you would repeat this until you've processed all the data. So batch is more like bounded or finite processing. Real-time is playing in the space of continuous, unbounded processing, but because you can also do reprocessing on a stream, it doesn't necessarily need to be real-time. You can also process historical data in a streaming fashion, for example. So this was a quick recap. And I want to finish this section by saying what could be a typical use case for stream processing in practice. This is an example that we will see later, and it is a very common one, which is you would collect data in real time, you would analyze it, and then you would display the data in real time. So that was a quick recap of what stream processing is. So let's talk about the 3 pillars of stream processing in practice. And here we'll cover some mind benders and also unlearn some bad habits. And we'll see what I'll mean by saying that. So the 3 pillars are the following. Number 1 is Kafka integration. The second is application versus clusters. And the third is streams and databases. So the focus here is on in practice. There are arguably quite a few key aspects of stream processing, but in this talk I want to specifically highlight those 3 because they are crucial in practice. That is to get stuff done right here and now. So the first pillar is Kafka integration. And why is that the first pillar? Why is this so important? So in our previous online talks, we've already covered this in more detail, but in summary, the industry is moving towards with data that is both big and fast. A streaming platform is the central nervous system of your company and its data, so it ensures that all this data can be shared fast, securely, and reliably across your organization, its systems, and its applications. This is what a streaming platform is and what it allows you to do. Now, in practice, of a streaming platform has become Apache Kafka. And Kafka is widely used in production at thousands of companies, lots more than fit on this slide. And many of these use Kafka at very large scale. So large number of applications, large number of engineers and data scientists using the platform, and hundreds of billions or even trillions of messages per day. Which brings me to scale. Some companies, such as Netflix, Microsoft, LinkedIn, process north of 1 trillion, so really like a lot of messages per day. But even so, Kafka is equally viable for small, medium, large, but also these extra large use cases. Similarly, and I alluded to that a bit at the very beginning when we were talking about cloud and on-premises, Kafka is also very popular for keeping the data flowing across an organization. And that means, for example, also to synchronize data between data centers, to migrate data from on-premises to the cloud, also to power hybrid cloud and on-premises setups, to help with disaster recovery, but also in situations such as mergers and acquisitions, where you need to integrate data across companies in a way that is reliable and real-time. So if Kafka is so important, if all your company's data is being shared through Kafka, and in practice the number of such companies is already large and still growing rapidly, then of course your stream processing technology must integrate well with Kafka. So the point is not just integrate with it, but integrate well with it. What do I mean with that? Integrate well means, first and foremost, it must be truly 100% compatible with Kafka. Now, historically, different stream processing technologies had better or worse records of Kafka compatibility, and some were even notoriously problematic. Kafka's recently introduced Streams API, of course, does not suffer from such problems because it's part of the open source Apache Kafka project and thus perfectly compatible and tested. So compatibility is very important. The second part is about getting data into and out of Kafka, so reading data and writing data. This must be done, in a fast and in a reliable way because the data is so important. Also, you want to have security functionality built in for a number of reasons, and we'll talk about that later on in a bit more detail. And the point here is that the easier security functionalities are being able to be used in your stream processing technology, the more likely they will actually be used in practice. And lastly, all of this functionality, all of this Kafka integration should be done in a way that it makes it a pleasure to use. It should be simple, easy, and fun, which is the point of something like a convenient API. And to give an example of what I mean by saying a convenient API, let's consider something like you have a stream processing tool and you write data from that tool to Kafka. What are the options currently? So I'll pick two examples here, and I'm picking Spark Streaming simply because it is a very popular one at the moment for doing stream processing. And this is the code that I want to highlight, and I will not talk about this in detail, where you have some piece of data, and I'm highlighting this with my cursor, which is a stream of word counts, a word and a count such as saying, Confluent 364. And you want to write this information after you have created the output data back to Kafka. So this is what the code would look like. The point here is that what we see here is that the execution model of Spark leaks into the processing logic. What does that mean? It means as a user, you must understand which part of your code runs here on the Spark driver machine versus the Spark executors in the Spark Kafka cluster. And frankly, this is not something that you even want to care about. The analogy would be you want to start your car by turning the key, but you must first assemble the engine yourself. Why is this so important? Well, it is important because in practice, your stream processing applications will do a lot of reading from Kafka and writing back to Kafka because this is the place where all the data is and where all the new data will need to go. So if this is not very convenient, you will have a lot of problems. Comparing this now to a different technology with a different API, here Kafka Streams API, you get the same effect with just this one-liner. Again, the point is not to compare Spark specifically versus Kafka specifically. It is about ensuring when you're doing evaluation that common tasks are easy and fun in your technology of choice. And also, going to this example that I'm showing on this slide, this code works equally well for data streams of a single message a minute or millions of messages per second. And this is something that you should strive for when you're picking your technology, that common tasks are simple, easy, and fun. The second pillar is applications versus clusters. The motivating example is questions such as, you need to do some stream processing and you're a fan of an architecture of reactive microservices. So you will wonder, well, which stream processing technology should I pick? And I'll try to address this question with the stream processing technologies into two main categories. They're the ones that follow the application model, or short, the app model, and then there are those that follow the cluster model. So I'll use the example that I showed at the beginning, which is a real-time dashboard for security monitoring. So imagine you're collecting data from your devices, mobile devices, IoT sensors, etc. in real time. You want to collect this into Kafka, you want to do some processing, and then you want to present the latest statistics and results, such as US East Coast is currently under attack, which is the big red circle that you're seeing on the screen. And you want to do this in real time. Now, depending on the category of tool that you're picking, how would such an architecture look like? So if you're following the cluster model, a very typical architecture is what I'm showing at the top here. So here you would capture events in real time into Kafka, then you would set up a processing cluster, like Spark, Storm, and so on. Then you would write and submit a processing job to that cluster, and then the processing results would somehow be stored into an external system or database. And then there would be a front-end dashboard application that would present the processing results to the end user by querying the database. What is the drawback of such an architecture? Because it does work. The drawback is, first and foremost, there is a lot of complexity embedded in here, and there are many moving parts. So it's not just that the architecture in general is complicated, but also like each individual piece is complex by itself. So oftentimes, such an architecture turns out to be more part of the problem than part of the solution. Now, if you contrast this to an application model for stream processing technology, you don't need a separate processing cluster, and it's some cases, and we talk about that later, you won't even need a database just to hand over data from your processing application to the displaying application. And by doing so, you can radically simplify this architecture into self-contained applications that, for example, you can deploy as containerized microservices. Lastly, there's also an interesting question that you can ask yourself here, and that is, spot the logical application that you need to implement in order to come up with this world map and real-time dashboard. I colored in blue color for both models where your application is. In the cluster model, your application is somewhere in your cluster, in the code that is the processing job. There's parts of it is in a database, and then there's also the front-end part. If you follow the application model, this is much more streamlined. So to juxtapose those different kinds, these different categories, in the application model, what you will be doing is you will write your stream processing pipelines as normal standard applications, like a normal Java application. In the cluster model, you would implement processing jobs that you would package and submit to a separate cluster. In the application model, you will not have a specific runtime because it is just a normal application. So for Java, for example, it would run on the JVM, just like any other Java application. For clusters, they have their own custom runtime. For example, Yarn, and you would need to understand Yarn before you would be able to use the technology. So this difference is kind of like the red thread between the models. So for the application model, you have these normal DevOps life cycles. You have clear ownership because you have much smaller pieces of things that you need to think about and worry about, and a similar architecture to begin with. Contrasting this to the cluster model, you have a very specific life cycle that is tailored to the technology. You have this split ownership, which I've showed visually in the previous slide with blue color. And you also typically end up with much more complex architecture because you need to stitch together different clusters, different systems in order to implement a given use case. Examples for these categories are on the application side. It would be Kafka and its Streams API, technologies such as Akka. And here we could say that you would get something like a cluster to go, which is functionalities such as elasticity, scalability, fault tolerance, and so on, without having to have a cluster, however. The cluster model, this Arc, Storm, Flink, and so on, where you always have to start with the cluster first, and then you would add your applications on top of that. Now, a black and white summary for what these models would typically be used for in practice by end users. So imagine you're a big retailer like, let's say, Walmart. You would prefer to use the application model for core business applications such as your real-time inventory management or order processing. And if these core applications would fail on Black Friday, you are in a lot of trouble. An analytics use case, on the other hand, would be something like shopping basket analysis. For example, figuring out whether a customer who buys diapers is also likely to buy beer, something that runs somewhere in the back end. Cluster models are typically very good at that for these analytical use cases. What we also see is that people that work in the line of business, that build these core business applications typically favor the app model more, whereas people that work on data infrastructure or business intelligence teams, like these shared teams that do, for example, data science, they favor more these cluster model, shared horizontal servers across the company. Now, even though I now contrasted these two models, of course, in practice, this is not an either-or decision. You can use both, and there are many good reasons why you want to use not just one of these technologies, but actually, two of them. Going back now to our original question as the motivating example for this section, if you want to build microservices, for example, clearly the answer would be, well, you would use a technology that allows you to think in this application model. The third and last pillar of stream processing in practice is streams and databases. So now this is a little bit of a mind bender, because the point is that in stream processing, you need more than just streams to get stuff done. As you've learned by now in this online talk series, streams are really everywhere. So I will not repeat the reasons why. If you're interested in that, now I refer to you to the previous talks that we had. The point that I want to make here instead is tables and databases are everywhere too. There is a reason why we have been leveraging databases and tables since decades. So I'll start with some examples that are very relevant in practice. Here I'm showing a use case where you have a stream and you want to turn it into a table. So for example, you want to build a customer 360-degree view. So you're getting information about your customers in real time through a variety of channels, mobile phone applications, your website, partner networks, and so on. And you want to consolidate all these different streams into a single consolidated view of your customer that is being updated and continuously in real time, which oftentimes is called a materialized view. So this is a very common use case. How would you use that in a stream processing technology in order to implement that? So here I'm showing how this would be done in Kafka and how you would use streams and tables in Kafka. So here the example is the word count example that I used earlier, where I'm moving my cursor again. Here's the first line that reads text lines from Kafka into a stream. And then there is the part at the bottom, which I'm highlighting with my cursor, that is doing an analysis by counting how often you have seen a given word so far. So for example, a text line could be hello world or hello Kafka. Be what you see on the right hand, the table that says I've seen hello 2 times so far. And the important point here is that as more and more data, more and more of these text lines are coming in, this view would be continuously updated in real time. So you would see hello being incremented to like 3, 4, 5, 6, 7, and so forth. So a very easy thing to do in a technology such as Kafka. Also, on top of that, once you have set up something like this, like this customer 360-degree view, you want to make this data available to other applications, for example. So if you're building microservices, you want to have other applications being able to directly query the application that generates the latest information for, well, the latest information. So that should be very easy to do as well. So similarly, there are situations where you have a table and you want to create a stream out of that. For example, you would have this customer 360-degree view, and as it is undergoing mutations, you want to capture all these latest changes into a changelog stream. In the database world, this is often called change data capture. And in this use cases of customer profiles, you might want to be able to alert based on certain customer events, such as the user has entered a new shipping address, and you want to make sure that shipments that are currently in transit are being routed to the correct address, and you want to do this as quickly as possible. So this is a situation where you would have a table and you would turn it into a stream. Then also very common is situations where you have a stream and a table and you want to combine them in the pipeline. So for example, you would have a table that is constantly being updated about all the passengers of your airline, and you want to get the latest information about these customers, and so you capture it into a stream, then you want to do the analysis on top of that stream to create another derived view, which would be, for example, all the passengers that are currently in transit to Europe that are at risk of missing their connecting flights. So again, you have tables and streams, and you combine them in your pipeline. The last use case I want to show here is streams and tables. Is oftentimes you have an incoming stream of of facts. That might be a very large incoming stream, for example, customer transactions. And then you would be joining these facts to dimensions such as customer profiles. So the result of that would be an enriched stream of information. So in summary, a stream processing technology must have first-class support for streams and tables. Why? Because most use cases in practice require not just one, but both. What is important is to understand that support or the lack thereof strongly impacts the resulting technical architecture as well as development efforts. So not having any such support means you have to do some painful do-it-yourself work, which typically means increased complexity and more moving pieces to juggle. So this was our first section on the 3 pillars of stream processing in practice. In this section, we will talk a bit about the key selection criteria. That will be the organizational, non-technical dimensions, as well as technical dimensions. So first, I just want to check with the organizers, because I got a message in chat that there might be a problem with slides not being advanced. So I just want to check whether that is still a problem or not.
It looks okay from us, Michael. We're sitting on the agenda slide right now.
Okay, sounds good. Then I will continue. So let's talk about organizational non-technical dimensions. So now we'll be very brief here. As I said, we'll be focusing on the technical functionality, but since it's a practical guide for picking technology, I also want to cover that very briefly. So a question that you would ask yourself here would be, can your organization understand and leverage the technology? So that could be a very subjective decision. Goes to familiarity with languages, other concepts, and if it's intuitive, are you able to get proper training for it, and so forth. There are also questions such as, are you being permitted to use it in your organization? Does it have the proper security features? What about licensing? Do we prefer open source versus proprietary licenses, and so forth? And also a more broader question, can you continue to use the technology in the future? So here, is the technology promising, and so forth? So we could turn this around and say, do you believe in the long-term vision? The reason why this question is important is because typically when you commit, you actually do commit, and you commit heavily. Switching technologies in an organization is often quite expensive because there is resistance to change. It takes a lot of effort to migrate applications, for example. So if you ask yourself the question, do you want to commit to a technology, be aware that almost anything is easier to get into than out of. Then you should wonder about, what is the path and time to success? Now, how easy is it to have an idea during lunchtime, and can you reasonably expect to have an answer whether that idea makes sense in general after an hour, or would it take you like a month to do that? And lastly, it's a bit about thinking out of the box, or like not trying to have tunnel vision. Think about whether there are areas that you could use that technology for in your organization that go beyond the current use case. Part of that is relating to, do you pick a technology that you can use more like generally, or is it more niche technology? Is it, for example, a technology that you can use also for like smaller or medium use cases, or only for the very large use cases, where you need to have a very huge minimum investment at the very beginning in order to be able to do your first use case? And then lastly, something that we already discussed, and that is about, do you prefer to build core business applications, or do you want to do more back-end analytics, for example? So here is like a quick composition of things that you might be asking yourself. It's again, there's some subjective questions in here, like what is the learning curve from an organization? Do we have good documentation examples to get started with? Is there a vibrant user community that we can get engaged with? Are there professional services and support from a vendor that I can trust, and so on? So as I said, quick overview, because we want to spend the time on the technical functionality. In my opinion, like most of what I've shown here is, transferable to any kind of technology that you're evaluating, so it's not specific to stream processing. So let's talk about the technical dimensions of picking a stream processing system. And what I'll do here is, I've selected 12 different dimensions, and I will briefly talk about each of them in turn. So let's start first with something that is more like higher level or conceptual. And let's start with state. Stateful processing is any kind of processing that requires, well, state. Now, in practice, most use cases for stream processing turn out to be stateful. So whenever you're joining something, whenever you're doing aggregations, whenever you're counting things, whenever you're doing window analysis, all of that requires state. So more often than not, the processing that you'll be doing is stateful. So proper support for state in the technology is very, very important. The first question that you would ask yourself is working with state performant? Is the state managed locally or remotely? For example, imagine you have an application that runs like in 3 instances, so it's the same application, and you have a very large incoming rate of events that you want to process. For example, 1 million messages per second. Now you need to do some processing that requires state, like counting things. How often have users clicked on my front page, for example? How often have I seen this customer buying something today? Now, if you pick a technology that requires state to be remote, then whenever you're doing stateful computation, you will be talking to an external database. For example, most streaming processing technology either lack any good state support, or most will support only remote state by relying on something like Redis as a separate remote data store. But a remote state has many drawbacks. Things like you run into things like increased latency because you have to talk across the network. You're also coupling the scalability and availability of your application with that of the remote data store. For example, if Redis is down, what are you doing? Do you wait until it comes back up? Do you buffer? What are you doing then? The opposite approach would be to kind of lift the state into your application where the state is local. So here we get the effect of highly performant local lookups and joins, even when we're doing this at very large scale. And even though that state is local, it is still fault tolerant, as we will see later. So here you're eliminating first the need for an external stateful, and you still get the benefit of fault tolerance, and scaling out. And lastly, just as a kind of a side note, oftentimes Kafka scales much better than any external data store that you want to use for stateful computations or storing some data. For example, Kafka can easily handle millions of messages per second, but can your external database like MySQL handle 1 million messages, 1 million queries per second if you want to enrich a stream with context information from your database? Of state management. The other question is about, is this state fault tolerant? And if it is fault tolerant, how fast is the recovery and failover? For example, in Kafka and its Streams API, an application state is automatically migrated from a failed client machine to a working client machine. How is this possible? Well, behind the scenes, any changes to the application state is automatically backupped incrementally behind the scenes to Kafka, so that once the migration happens to a new machine, this backup can be restored to the machine to bring back the state in exactly the state it was on the original machine. And lastly, because a lot of the value of your applications will be in the state, is this state readily accessible from other applications? So we talked about that earlier when I mentioned interactive queries. So this functionality is already available for general use in Kafka. Other technologies such as Spark and Flink are currently developing that as well. And there are some others where it's not yet available. So as a reminder, what is interactive queries? Here, your application manages some state, computes, for example, current passengers in transit, and you want to expose this information directly to other applications so that they can use it right away. The next dimension is abstractions. So here we're asking, what is the data model and what are the available abstractions in my technology? So most commonly in stream processing, the abstraction that you have access to is a stream of records, events, and messages. This is basically supported by all technologies nowadays. However, a recent addition, and arguably a very powerful one, because we talked about this earlier when we talked about the 3 pillars of stream processing, there's also a table of records. At the moment, this is currently unique to Kafka, but other projects are also thinking about adding that. And as a reminder, the table would be something that represents the latest state or materialized views of your applications. And we've argued that state must have a first-class abstraction because, as we just saw previously, it is crucial for. So if you're picking a technology, you should ask yourself, what is the data model? What are the abstractions? And can I make use of them in a way that is simple, easy, and fun? The next dimension is the time model. So what is important to understand here is that different use cases require different time semantics. Now, in general, the great majority of use cases require event time semantics, and I'll explain that in a second what that is. Other use cases may require processing time, for example, when you're doing real-time monitoring, such as the example that I've showed earlier, or some specific, more niche variants like. So when you're picking your technology, you should look for one that at a minimum supports event time, because that means you are able to cover most of the use cases in practice. Now, what is that? Here, the canonical example, I think, is the Star Wars franchise, where you have, a list of episodes such as The Phantom Menace and Attack of the Clones. And in terms of the time when things happen in the Star Wars universe, the first episode was The Phantom Menace. However, in terms of processing time, we are looking at the time when the film was actually aired to the public. And here, the 4th episode, A New Hope, was the first one that was available in the 1970s. Now, in practice, typically, you want to work on data in the order they were generated in their own universe. So, for example, if an IoT sensor sends you information about temperature, you want to do analytics on that information based on the timestamp that the sensor provided to you, and not the time that you happen to process the data in your data center, because these different notions of time will vary widely in practice. It is also key to differentiate between event time and processing time if you ever need to reprocess your data. Imagine you have 1 month worth of data and you need to reprocess it, for example, because you fixed an application bug and thus you need to regenerate the data again. If you reprocess it a month later, you don't want the application to think that all this 1 month worth of data has just arrived today. The next dimension is windowing. Windowing is an operation that groups events. So, for example, you might get data arriving like in all kinds of order. So we talked a bit about the time semantics in the previous slide. And what you want to do is you want to group it together so that related events are in the same bucket. So, for example, here what we're showing is you're kind of bucketing events by user based on time windows. Most commonly in practice, you need 2 kinds of windows. One is time-based windows, and the other is session windows. An example for these 2 would be real-time monitoring. You typically do things like 5-minute averages and statistics where we'd use time-based windows. Conversely, you might have a different use case where you want to do something like reader behavior analysis on a website such as the New York Times. Here, you want to think in terms of users interacting with your website, and you might consider clicking on my website at least once per minute. The user is continuously using my website in a single session. If the user stops using my website for, let's say, 30 minutes, I consider that the next click would be the start of a new session. So visually, I'm only showing time windows here, is you might want to do something like tumbling windows where you split your stream into separate fixed-size chunks based on time. And typically, another variant of such time-based windows are hopping windows, where you kind of hop these windows forward in time to say something like, I want to have 3-second averages, but I want to get an update on the latest average that was being computed every second. The next dimension is out of order and late arriving data. So this ties back into what we talked about earlier about the time model and also when we talked about windowing. Here, the first thing that I think one should understand is that out of order data and late arriving data is not a corner case. It is actually very common in practice. So I think a very easy example of such a situation would be the following. Imagine there are users that have mobile phones and they enter an airplane, and quickly after takeoff they will lose internet connectivity. Now, while they're on their intercontinental flight, they might write emails, use applications, and so forth, and it will take a long time until they're back in their destination when they get back internet connectivity, and all these phones would start sending all the cute emails that were written during the flight. So what you have here is that data was being generated event time during that flight, during these 10 hours, but they will be sent only after the airplane has landed. So they will arrive with a significant delay in your data center when you want to do processing. So what we want to get out of a stream processing technology is very good control over how such out-of-order late data is being handled. For example, imagine you're processing data in 5-minute windows, for example, to compute statistics, averages, or total number of orders. And we want to be very explicit in saying that, for example, when an event arrives just a single minute late, we want to update the original result for that 5-minute window with the latest information. However, at some point, we want to define that, okay, if it takes too long for such data to arrive, then you want to throw it away. For example, if after 2 hours there is still not an event that should be included, we just consider to discard it. Now, apart from being able to control it and to define explicitly when events should still be considered for further updates or when events should be discarded, all of this must be done in a very efficient manner behind the scenes because it just happens so often in practice because of network glitches and so on. So this should not be an afterthought, it should be like an integral part of your stream processing solution. The next dimension is reprocessing. So oftentimes you want to reprocess data by rewinding a stream back in time. Use cases in practice include fixing things that went wrong in production, or facilitating iterative and explorative development. You want to try out an idea, see what the result is. Maybe you don't like it and you want to rewind back in time to use the same data for the next attempt. This again leads us to things like A/B testing, where you want to point to different variants of the same application to the same starting point in a stream and see whether one comes up with a better result than the other one. So these are just a few examples here. Now also, the reprocessing functionality might on the one hand be exposed to you as the user for your own applications, but often it is also being used behind the scenes for fault tolerance, for example. So if a machine fails, a new machine that will take over the work might want to rewind in time in order to fix the stuff that happened in between the crash. So as we've seen earlier, if you have a streaming platform like Kafka as the store and source of your data, you can easily support because the foundational storage layer of your streaming platform is able to provide you with this rewind back in time functionality. So the next dimensions are scalability and elasticity and fault tolerance. And I want to talk about these two separate dimensions together because they are very intertwined. So questions that we want to find answers to here are, can the technology scale according to our needs? Is it able to give us the required latency? What about the throughput? For example, is it able to process millions of messages per second? Also, and that is related to scale, but not in terms of like the high end, but more like the low end. The question is, what is the minimum footprint? Like how much money or how much effort do you need to spend in order to get started with it? Will it work just for the very large use cases because it's just so complex to set up that I don't want to go through that pain for like the smaller use cases? Or can I use it like across all the use cases that I might have in my company? Also, and this is more about elasticity, is the technology able to give you expand and shrink functionality when you need to tune the capacity of your applications? And can it do so at runtime during operations? This is important for a number of reasons, partly because you might realize that, well, there is an increase of popularity for my product, so I just need to add more hardware and more capacity to my application to keep up with the increased demand. But it also helps with resource utilization and optimizing for that, because in practice, most streaming applications will run continuously. So this typical real-time scenario. So that means once you give resources to your application, it will continue to use it as long as it's running. So being able to dynamically expand or shrink your application allows you to free up resources if, for example, there is not as much input data as you expected. And lastly, there is the category of resilience and fault tolerance. So you should ask yourself questions such as, what kind of guarantees do I have for data delivery and for state? Do I need at least one semantics? Do I need even more, such as exactly one semantics, and so on? You should also figure out what your needs are in terms of failover behavior and recovery time. Is recovery, for example, automated or is it manual? And also, is there any negative side to enable fault tolerance functionality? In a technology such as Storm, where users can opt to enable so-called hacking in order to be able to figure out which messages have been processed and which have not. Enabling this functionality typically results in a very big performance hit. So I want to figure out whether and how much this is important to you. Most probably it is important. So to show some of this elasticity part in some visuals, imagine you have an application and you realize that a single machine is not able to handle the load. Can I just start 2 additional machines and they will start automatically sharing the work for doing that processing? And we talked about state earlier. Does this also work for any state that is being done? Because what will need to be done then is by the technology is to migrate parts of the state to these newly added instances of your application so that they can continue exactly where the previous original single instance left off. And similarly, as soon as you want to shrink this example, you need, again, migrate input data and accumulated state into the remaining instances. And all of that should be seamless without you having to do anything other than making the decision how much capacity you need. The next dimension is security. Why should you worry about security? Well, there are a number of good reasons, but I just mentioned a few of them here. So oftentimes you have internal security policies that you need being enforced by your information security team. You might be subject to legal compliance and regulations. It's a very broad area, but I think typically there are 3 basic requirements for stream processing applications. The first is being able to encrypt data in transit. For example, when you're reading data from Kafka or writing data back to Kafka. You also want to have authentication so that you can enforce, for example, that only certain applications may talk to the production environment. And lastly, authorization, where you can say, for example, we have some information in Kafka that is quite sensitive. It might include personally identifiable information, and we only want to give certain applications access to the sensitive data. And lastly, there's oftentimes a trade-off between security and convenience, but even so, what's important is that the technology that you want to pick is one where it is easier to use the security features, because the easier that is, the more likely they're actually being used in practice. The next dimension is the processing model of the technology. Here, true and native stream processing is record-at-a-time processing. So if you get a message, this message is processed in its entirety in order to get benefits such as low latency processing results in the order of milliseconds, and you can also deal very efficiently with out-of-order data. Now, you said that out-of-order data is actually a very common case in practice, so true stream processing is very good at dealing with that because it processes records at a time. So I'll not go into too much detail here why that is actually the case, and why stream processing is very good at that, because we lack the time. But we have some other resources that we can point you to if you're interested in that. Also, what is important to understand is that oftentimes you need to make trade-offs between latency and throughput. But even so, modern stream processing technologies can provide both low latency and high throughput through internal optimizations such as very smart buffering and so forth. So in examples for stream processing technologies that are really not doing true stream processing, record at a time, are Kafka, Storm, Samza, Flink, or Beam. Then there are some other processing technologies that opt for batching or micro-batching. So micro-batching, I think, has no true benefits. There is no reason why you would want to use micro-batching other than, well, it's just the way it works in the technology. Typically, I would consider it more like a technical workaround to shoehorn stream-like functionality into a tool. And why do you not want to use micro-batching in the first place? Well, typically it suffers from significant overhead. For example, when dealing with out-of-order and later writing data, or when you're performing a node analysis. Because you don't just have to fix a single message that is arriving late. You actually need to fix and reprocess a bunch, like a batch of all these messages. And if that happens very often, which is the case in practice, there's a big performance hit. So what does that mean in the end? Well, typically, micro-batching based tools are a strong blocker for use cases where you really worry about low latency, such as fraud detection, where you want to make very quick decisions. And here, like low latency, it's something where you think in terms of like a few seconds and faster. So it's not just like talking about a few milliseconds, but sometimes a few seconds. This is prohibitive. Now, an examples for technologies that are micro-batch or batch-based are Spark or Storm's Trident API. And I'm also including Hadoop here because Hadoop is also batch. And we could also conceive that if you just run your Hadoop jobs very quickly on small pieces of chunks, you also get some kind of micro-batching, which is actually the approach that Spark went with, albeit at a much more granular manner than what you would be able to do if you were to use Hadoop for that. The next dimension is API. So when you pick a technology, oftentimes the choice of the API is a highly subjective matter. It depends on existing skills in your team. It might be strong preferences. It might be different whether you're looking for a tool that can be used by the core business analysts and so forth. It might also be depending on which tools you want to integrate with that are already existing in your company. So typically, tools give you the following options. You can either have a declarative expressive API, which is a bit like functional programming, where you can do operations such as map, filter, reduce, join. Then there are APIs that are more imperative, lower level, where you typically get like callbacks with functions such as a process function. It gets an event, and then you do like low-level operations on top of that, which is a bit like a sampler. So to speak, if we compare that to these previously mentioned declarative API. And lastly, the third main option is SQL for the streaming world, where you use a typical SQL statement but adapted for the streaming world. Now, in the best case, you not just get a single one of these APIs, but all three of them, preferably. But again, your mileage may vary. It is really often like a subjective decision. Now, lastly, after this brief overview, there are also like two notions. First, oftentimes abstractions, like a declarative API, are really, really great because you don't need to worry about any of the internals. You just want to, tell the computer what you want to have as the result, and the computer figures out how to do that. On the other hand, sometimes abstractions are actually quite horrible because they're hiding too much. So they're creating kind of artificial barrier between what you want to do and what is actually going on behind the scenes. And for quite a number of use cases, you want to know exactly what is going on, for example, because you're at a very large scale or because you want to do something very specific to your application use case where things like map and filter are not expressive enough. So you need to tinker with your application on a lower level. So this, again, is a trade-off. Typically, what we've seen is that people prefer these declarative APIs or SQL use cases where you need to fall back to an imperative API, if only to come up with functionality that is not yet available in these declarative APIs or not yet available in the SQL interface for the technology. So the last dimension that I want to briefly cover is the look and feel and the way you interact with that technology in your daily work. So the developer and operations lifecycle. So here we want to ask questions such as, if I want to do quick iterative development, like I modify my code, I want to test whether it is better now, and then I'm going to repeat that cycle until I'm happy with the results. Is that easily doable with that technology? If I want to decouple teams and project schedules, is that working well? Is it a bit more difficult with a shared horizontal cluster, or would I rather prefer to have like this application model where each team can build their own application, basically not thinking about any other teams and what they're doing? And here, again, there's this big difference between the technologies that fall under the category of the application model and those that fall under the cluster model. The difference is that the way you test your applications, the way you package them, deploy them, monitor them, and operate them, it's greatly different between these two models. For example, you might ask yourself the question, do I need to know Java, which is the app model, or do I need to know some specific technologies such as Yarn in order to get started with this use case? Similarly, you may have the desire to say, I want to do some reactive processing with Docker containers, and I want to run this on Mesos or Kubernetes. Which of these can I use, and how does it feel working in this environment with that technology? Similarly, you're not deploying an app one time and then it's good. What you want to do is you want to maintain your application moving forward without a lot of pain. So, for example, we should look for features that allow us to rolling, no downtime upgrades, for example. We should also ideally have a technology that is able to integrate well with your existing operations infrastructure, tools, processes, and so forth, so that the stream processing part that you're using in your organization is not the social oddball where you need to look for exceptions. Hey, can I do this? It's typically not allowed because we have our standards, but this technology forces us to follow a certain path, and it forces certain rules upon us. So you want something that integrates well with what you already have. So in summary, I would recap as follows. What we covered here, I think, is a good starting point for selecting your stream processing technology in practice, but unfortunately, there is no free lunch. There is still a lot of work that you need to do. First and foremost is figuring out what you really need and weigh the criteria appropriately. I would also encourage you to think end-to-end. So if you pick a technology, you should think about things such as, if I have an idea, how fast can I actually come up with a first proof of concept of that idea in terms of development and testing and so forth, and put it in production just to see whether it works or not. And also, if it is in production and it does not do what I want, if it fails, if it's not fast enough, if it's not computing the correct things, can I troubleshoot and debug, do that locally to replicate that, or is it just hard to do any kind of local troubleshooting because you always need to have like a large environment of things to set up in order to make sense of it? Similarly, I would also encourage to think not just in terms of, let's say, how many lines or how few lines of codes you would need to implement a use case, but also think about what could you use the technology for in a company that goes beyond the specific use case at hand. Is it a broadly applicable technology, or is it more niche technology? What is the impact of the technology on the overall architecture? Not perhaps for single use cases, but for use cases in general, for the environments that you're running it in. What is the security story of the technology? Can I get trainings and so forth? And lastly, there are these do your own thing. Do your own internal hackathons. Do your own kind of A/B testing of tools. Pick a simple use case, one that is hopefully representative of what you want to do. Implement it in 1, 2, 3 candidates and see which you would prefer running and supporting in production. And also, I just want to call this out specifically, oftentimes people ask the question, well, can you process X messages per second? And then there are benchmarks that say, yes, you can, or yes, you cannot. Most likely, you will need to do your own benchmarks. First, because you can trust your benchmarks that at least there was no inherent bias in them, but also because use cases vary widely, and it's hard to find a benchmark that really matches the one that you would like to see. Now, if that all sounds like too much, I would recommend a recommendation, and that is, if in doubt, pick something that is similar rather than something that is more complex or fancy. Why is that? Well, based on practical evidence, simple means things are faster to learn and understand, they are less likely to fail, and so forth, easier to debug. So if you are weighing your decision between two different technologies, if one is similar than the other, this is a good indication that it's perhaps the better one. So I think we covered a lot of ground so far. So we still have a few more minutes now for questions and answers from the audience. So I hand over now to Clark. Clark, feel free to start our Q&A session.
Hey, Michael, we're actually over time at the moment. So what I'm going to propose is we do have a few questions. Is we do a follow-on blog to kind of address some of those as it applies to the content that you covered. I think this was extraordinarily thorough. There's a few inquiries around, if I'm using Kafka for pipelines, but I have another streaming capability, how do I go about reconciling that moving forward, inclusive of migration and whatnot. So probably a little bit more involved than we can cover here at this point, but I propose now. So I want to thank you. This is very, very informative. I hope everyone enjoyed the webinar today. There will be a recording in case you showed up late or you missed part of it partway through. So look for information from that. Michael, can you just forward one slide, please? We do have one more session in this series about streaming. And think of it as a holiday present from us on December 15th. We're going to talk about streaming in practice and talk specifically about what this starts to look like in production. So hopefully you'll be able to join us then for that session. So with that, I'd like to call today's webinar a wrap. And I want to thank Michael, and I want to thank you all for joining us, and hope you all have a great rest of the day.